All right, so in this first topic, we're going to discuss what function notation is. And so in order to do that, take a look at our canvas. Now I have four equations here. They're not intended to be related in any particular way. I have also listed them in all the same color to make a point, which is if I were to say, hey you over there, check out that function, you would have no idea what I'm talking about because there are 4 functions on the screen and I have given you no way of knowing which function I'm talking about. Now I could say look at that function on the top or look at that function on the bottom, although again if I say look at that function in the middle you would say I still don't know which one you mean because you might mean y equals -1/2 x plus 10 or you might mean y equals 3x. So I suppose I could just say, well, what I meant was y equals -1/2 x plus 10, but I hope you notice that gets to be a bit of a mouthful. It seems a little bit annoying, for lack of a better word, that when we're looking at these functions, I have no clear way of explaining to you in a very brief way which function I'm talking about. And that is where the concept of function notation comes in. So function notation says, instead of naming all of our equations in the same way, let's take away, I'm going to go over here, let's take away the y's and let's replace them with something a little more identifiable. So for instance, this first function I'm going to call the f function. The second one I'm going to call the g function. And then the h function, and I'm going to say j because we often use to mean other things in math, so I don't want to be confusing by saying I. So, and it also looks a little bit like a 1. So f, g, h, and j. Now, when we use function notation, and we call it according to a letter, we also I'll write it like this, and then I'll tell you what it means. It's going to kind of look like I'm trying to multiply, but this is not multiplication. This is notation. In other words, it's a language for talking about functions. So notice for each of these, I've put an x in parentheses. Each of these statements, this is called f of x, this is called g of x, h of x, and j of x. So the term of means I have a function that we're going to call f, where the variable is x. And again, I have a function I'm going to call g with a variable of x. A function h of x means a function h with a variable of x. J of x means a function j with a variable of x. So those 4 labels are really just that. They aren't, it's not multiplication. I'm not changing the variables around. I've just, instead of having y to explain the output, because that's what usually we mean by whenever we use the letter y, we mean that's the output value of the equation. Instead of using y for everything, because then that just creates confusion as to what we mean by that equation or that function whenever we're talking about them, we're going to name them. But when we name them, we name them according to a letter and also according to the input variable x. F of x, g of x, h of x, j of x, or anything else. It could be m of x, it could be q of x. It doesn't matter what letter we use. It does matter that we say x though, because x is our variable in each of these equations. So looking back at the equations, my voice is cracking on me for no apparent reason. Probably means my son shared his cold with me, so I apologize. Okay, looking at these functions, I want to talk about how this is going to be useful to us or how we use function notation. Well, one way that we use it is to be able to input a number into the equation. Kind of like, think of the equation like a little machine. It's a number machine. What we put in is an x value. So let's say I wanted to put the number 1 into the function f. So the way that we'd write that is we'd say let's put 1 into f. So instead of writing f of x, I've written f of 1. So if you want to remember what that means, f of 1, that's how we read that. F of 1. And what does that mean mathematically? Well, it just means let's take the equation 2x plus 5 and let's solve it with 1 instead of x. So it would be 2 times 1 plus 5, which is 2 plus 5 is 7. So f of 1 is 7. Or I could say, let's find h of 4. Well, that means we go to our list here. We say, oh, not f, not g. Oh, we have h. This label, this notation means we want to take the function h and we want to input 4. Input 4 into the equation. So the equation here is 3x, right? That's what h is. So instead of 3x, we say 3 times 4. And the answer is 12. So that gives you an example of one way that we can use function notation. That's not the only way. Another way we can use it is to combine functions. So suppose f and g are two equations that relate to maybe production at a company. So f of x describes one type of production. Maybe it's like their revenue, the money that they're bringing in, and maybe g of x represents the cost of making the products. And I say, I just want to put those two functions together and find out how much money we're making. And so I would say, I want to take the f of x equation and I want to add it to the g of x equation and find out how much money we have in general. So we'd write out f of x plus g of x. And all that means is that we take the f of x function, which is 2x plus 5, and it means I add it to the function g of x, which we know is negative 1/2. Now I'm going to put it in parentheses so that, actually I'll put both of these in parentheses. You don't have to, but it helps us to see the two different pieces. And in the second case, you don't want to mix up the plus sign and the negative 1/2 here. So we have 2x plus 5, which is my f function, and negative 1/2 x plus 10, which is my g function, and I want to add them together. Well, first thing we do is we're going to go through our hierarchy of operations, parentheses, multiplication and division, parentheses, then exponents, then multiplication and division, then addition and subtraction. Parentheses, is there anything I can combine in the parentheses? No, there's nothing I can simplify, so I leave that alone. I ask myself, are there any exponents I can simplify? No, because I don't have any exponents, so I can move to the next one. Multiplication, nope, there is multiplication, negative 1/2 times x, but you're not going to simplify it any further than that. So the last thing I do is I just add. So I'm going to take 2x plus 5, and I'm going to add to it negative 1/2, which would be like minus 1/2 x, and I'm going to add to it 10. So I'm just simplifying the equation here. Combine like terms, 2x and negative 1/2 x, I can put those together to be 1.5 x. For those of you who like decimals, I'll actually say 1.5 x. And then plus 5 and plus 10 can become plus 15. So all I've done is I've just taken the terms here and I've combined the like terms. I've added them together because I wanted to know what it meant to get f of x plus g of x. And now we know. It means 1.5x plus 15. That is another example of how we use function notation. Now, I'm going to erase this here for us for a second. I'm just going to delete all of it little by little. It's the quickest way. And I'm going to show you an example. We're not going to solve all of these, but I'm going to show you examples of other, we'll keep that, other function combinations we could use. So we just did f of x plus g of x. But we could do maybe h of x minus j of x. Or I could do f of x times h of x. Or I could do g of x divided by j of x. So all these are different. I mean, I could go on and on with different combinations. My point is, any mathematical operation that I could do between numbers, I can also do that to functions. And all that I'm doing is just taking the information. So if it says f of x, I'm just going to replace that with 2x plus 5, which we just did, 2x plus 5. And then it says plus g of x, so I replace that with plus negative 1/2 x plus 10. Same thing for the subtraction example, except that I'd make sure to use the information from h of x, which is 3x. And then I would subtract from that j of x, which is x squared. I have f of x times h of x, so that would mean I would take 2x plus 5 and multiply it by 3x. You have to use a little bit of the distributive property for that one. I'm going to collapse that for us, because we'd have to take 3x and we'd have to distribute it to 2x and to 5. But that would be a multiplication example. Or a division example would be negative 1/2 x plus 10, that's the value of g of x, over x squared. In other words, we're just creating, we're taking the expressions that are on the right side of these functions, and we're performing operations on them. Not like medical operations, like mathematical operations: addition, subtraction, multiplication, division. So those are all ways that we can use function notation. Now, I am not completing these problems right now just because we're going to spend time in class doing that. But we would want to simplify, like I did in that first example. You don't want to leave, and for example, up here on the f of x plus g of x, you don't want to leave all these terms when there's so many like terms. You want to try to simplify it down to something that looks a little bit nicer. However, on something like g of x divided by j of x, which we can talk about more in class, we would find, if we examine that we really can't simplify it. It has to stay the way that it is. So that is sort of a second step. It's not necessarily part of the function notation definition, so we'll save that for class time. So let's review just quickly before we move on to topic 2. Looking at what function notation is, we can use letters to name functions so that we don't get them confused. We can then use that information to write something like, here in the blue at the top, f of 1 or h of 4. Basically, it's a code for telling us what number to input into which function. Or you can look down in the lower right where we have function notation that shows us how to perform mathematical operations between multiple functions. All right, so we're going to stop there, and then we will pick up in topic 2 and talk about something called compound functions.